The video illustrates a high-level architecture for developing and deploying a large language model, LLM, specifically designed to handle organization confidential data and information. Let's break down each stage in the context of this sensitive application. Pradeep K. Suri, author, researcher, consultant, and AI/ML architect. Data ingestion, blue. This initial stage involves collecting and bringing together the organization's confidential data. For an LLM dealing with sensitive information, this step is critical. It requires robust security measures and access controls to ensure only authorized data is ingested. Anonymization or pseudonymization techniques might be applied at this stage if permissible and beneficial for downstream tasks while protecting privacy. Pre-processing, red. Once the data is ingested, it undergoes pre-processing to prepare it for training. This typically includes cleaning, removing noise, errors, inconsistencies, tokenization, breaking down text into smaller units, and potentially masking or redacting highly sensitive information that the model shouldn't directly learn or output. The choice of pre-processing techniques is crucial to balance model performance with data security and privacy. Training, green. This is where the LLM learns from the pre-processed confidential data. For organizational confidential data, training might involve techniques like fine-tuning a pre-trained LLM on the organization's specific data or even training a model from scratch, though less common due to resource intensity. Security and access control remain paramount during training, and techniques like federated learning or secure multi-party computation could be considered in highly sensitive scenarios. Model evaluation, yellow. After training, the model's performance is evaluated. In the context of confidential data, evaluation goes beyond standard metrics like accuracy and fluency. It must also assess the model's ability to maintain confidentiality, avoid data leakage, and respect privacy constraints. This might involve specific evaluation metrics and red teaming exercises focused on identifying potential vulnerabilities related to sensitive information. Deployment, purple. This stage involves making the trained LLM accessible for use within the organization. For confidential applications, deployment likely happens within a secure, controlled environment with strict access controls and monitoring. Considerations include how users interact with the model, logging of interactions, with appropriate anonymization if needed, and preventing unauthorized access to the model's capabilities. Monitoring, pink. Continuous monitoring is essential after deployment. For an LLM handling confidential data, monitoring focuses not only on performance and reliability but also on detecting any potential security breaches, data leakage, or unintended disclosure of sensitive information. This includes monitoring user queries, model outputs, and system logs for any anomalous activity. In essence, the architecture highlights the standard LLM development lifecycle, but with a strong emphasis on security, privacy, and control at each stage due to the confidential nature of the data being handled. The narrowing flow visually suggests that as the data and model progress through the pipeline, specific considerations and constraints related to confidentiality become increasingly important. This image illustrates the structure of a deep neural network, DNN, that could serve as the underlying architecture for the AI agent, specifically in the context of a large language model, LLM. Let's break down the components. Input layer, on the far left. The input layer represents the initial data fed into the network. In the context of an LLM, this input could be a sequence of words or tokens that form the text prompt or query given to the AI agent. Each node in the input layer would typically correspond to a specific feature or element of the input sequence, example an embedding of a word. Hidden layers, hidden 1 to hidden 5. These are the intermediate layers between the input and output layers where the actual deep learning takes place. The image shows 5 hidden layers, but real-world LLMs often have many more, hundreds or even thousands. Transformation and feature extraction, each hidden layer consists of multiple interconnected nodes, neurons. These neurons perform mathematical operations on the inputs they receive from the previous layer, applying weights and activation functions. Through these operations, the network learns to extract increasingly complex and abstract features from the input data. For an LLM, earlier hidden layers might learn about individual words or short phrases, while deeper layers can capture more intricate semantic relationships, context, and even high-level concepts. Hierarchical representation learning, the depth of the network, the number of hidden layers, allows the LLM to learn hierarchical representations of language. Lower layers learn basic linguistic features, and subsequent layers build upon these features to understand more complex patterns and dependencies in the text. Output layer, on the far right, the output layer produces the AI agent's response. For an LLM, the output could be a sequence of predicted words or tokens that form the answer, continuation, or generated text. The number of nodes in the output layer and their activation function depend on the specific task. For example, in a language generation task, the output layer might have a node for each word in the vocabulary, with the activation indicating the probability of that word being the next in the sequence. Connections, white lines. The white lines represent the connections between the neurons in different layers. Each connection has an associated weight, which is a numerical value that the network learns during the training process. These weights determine the strength of the influence of one neuron on another. DNN for AI agent, LLM, implications. Complexity and capacity. The deep architecture with multiple hidden layers allows the LLM to model the intricate patterns and long-range dependencies inherent in human language. The large number of connections and weights gives the model a high capacity to learn and represent vast amounts of linguistic information. Learning representations. Through training on massive text data sets, the DNN learns distributed representations, embeddings, of words and concepts in the hidden layers. These embeddings capture semantic relationships and allow the model to understand the meaning of words and phrases in context. Sequence processing. While this diagram shows a general DNN structure, LLMs often utilize specialized architectures like transformers, which are still deep neural networks but have specific mechanisms, like attention mechanisms, designed for effectively processing sequential data like text. These mechanisms allow the model to weigh the importance of different parts of the input sequence when generating the output. Scalability. The performance of LLMs often improves with the size of the model, number of layers and neurons, and the amount of training data. This scalability is a key characteristic of deep learning. In summary, the DNN structure depicted is a fundamental building block for an AI agent powered by an LLM. The depth of the network enables the learning of complex linguistic features and relationships, allowing the agent to understand and generate human-like text. While the diagram shows a basic feed-forward DNN, modern LLMs often employ more sophisticated architectures built upon this foundation. Thank you.